You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Cloud Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. VPN protocols serve as the foundation for secure and reliable communication across distributed networks. In cloud environments, these protocols determine how encrypted tunnels are formed, authenticated, and managed. Choosing the right protocol affects everything from performance and interoperability to regulatory compliance and cost. In the context of the Cloud Plus certification, protocol selection is not only a technical decision but also a strategic one. Understanding the underlying mechanics of VPN protocols helps ensure successful deployment and long-term reliability. IPSec and MPLS are two widely used technologies that offer distinct benefits and serve different purposes within cloud architecture. IPSec, or Internet Protocol Security, provides encryption and integrity at the network layer, allowing data to be protected as it travels across untrusted networks. MPLS, or Multiprotocol Label Switching, is designed to route data efficiently through large-scale networks by using labels instead of traditional IP-based routing. The Cloud Plus exam places significant emphasis on understanding both of these protocols and when each is appropriate. IPSec is a suite of protocols used to secure IP communication through encryption and authentication. It includes components such as the authentication header, encapsulating security payload, and Internet key exchange. These elements work together to ensure confidentiality, integrity, and secure negotiation of cryptographic parameters. IPSec operates at Layer 3 of the OSI model, meaning it functions independently of application data, making it suitable for securing all network traffic regardless of the upper layer protocol. There are two modes of operation in IPSec: tunnel mode and transport mode. Tunnel mode encrypts the entire IP packet, including headers, and is commonly used for site-to-site connections. Transport mode encrypts only the payload, leaving the headers intact, and is more often used in end-to-end or host-to-host communications. In cloud environments, tunnel mode is preferred because it allows full encapsulation and is compatible with virtual private network gateways. Understanding these modes is essential for configuring VPN tunnels that align with enterprise security requirements. Internet key exchange, or IKE, is the mechanism by which IPSec peers negotiate cryptographic keys and policies. The exchange can be authenticated using pre-shared keys or digital certificates, and successful negotiation results in the creation of a secure tunnel. Failures in IKE negotiation are common causes of VPN instability and are usually linked to mismatched configurations or certificate issues. Proper understanding of key management and authentication options is essential for Cloud Plus candidates deploying IPSec in real-world environments. IPSec is widely used in cloud networking to secure traffic between cloud resources and on-premises infrastructure. It is the default protocol for many site-to-site and point-to-site VPN implementations. Cloud platforms typically provide native support for IPSec through their virtual network gateways. IPSec is often selected for its robust encryption and standards compliance, making it well-suited for industries with strict regulatory frameworks. Its flexibility allows it to support both static infrastructure and dynamic user-driven access. While IPSec provides strong security, it also introduces processing overhead due to encryption and decryption. This overhead can impact performance, especially in high-throughput environments or when using software-based VPN gateways. Hardware acceleration, such as cryptographic offloading on dedicated appliances, can improve performance. Additionally, tuning parameters like packet size and maximum transmission unit settings can help reduce fragmentation and improve throughput. The exam may include performance trade-offs that influence protocol selection or hardware configuration. MPLS is a routing technology that uses labels instead of IP addresses to direct traffic through a network. Labels are assigned when a packet enters the MPLS network and are used to determine the path it should follow. Because routing decisions are made based on labels rather than table lookups, MPLS reduces latency and increases predictability. This makes it ideal for large-scale networks, including those operated by cloud providers and telecommunications carriers. Label-switched paths in MPLS allow administrators to predefine how data moves through the network. This control enables efficient bandwidth usage and traffic prioritization. MPLS uses the concept of forwarding equivalence classes to group similar traffic types, which are then treated consistently throughout the network. This structured approach to routing supports high availability and ensures that mission-critical traffic receives consistent quality of service. Cloud Plus candidates should understand how label assignment and path definition work in MPLS environments. MPLS also integrates quality of service mechanisms, allowing for precise control over traffic prioritization and bandwidth guarantees. Labels can be associated with specific service classes, enabling network devices to treat high-priority traffic, such as voice or video, differently than bulk data transfers. This capability makes MPLS ideal for real-time applications that are sensitive to latency, jitter, or packet loss. The exam may test your ability to identify use cases where advanced quality of service is a deciding factor in protocol selection. Cloud consumers typically access MPLS services through agreements with telecommunications providers. While they do not configure label switching paths directly, they must understand how those paths are provisioned and how service-level agreements define performance and availability expectations. In contrast to IPSec, where the consumer manages encryption and peer settings, MPLS environments are largely controlled by the provider. Knowing these boundaries helps candidates answer exam questions that involve provider-managed wide-area networks. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Comparing IPSec and MPLS within cloud deployments requires an understanding of their strengths, limitations, and operational models. IPSec is typically implemented directly by the cloud consumer, who manages the encryption, authentication, and routing. It's favored for securing data over untrusted networks such as the public internet. MPLS, on the other hand, is usually delivered by a service provider and focuses on performance, reliability, and traffic engineering. In most cloud scenarios, IPSec addresses security, while MPLS optimizes transport. In hybrid networks, organizations may use both protocols simultaneously. A common model involves using MPLS as the core wide-area network backbone between offices or regions, while layering IPSec tunnels over that network for end-to-end encryption. This approach combines MPLS's low latency and quality of service with IPSec's strong confidentiality and authentication. Candidates must understand how hybrid models can leverage both technologies to achieve robust, secure, and high-performance interconnectivity across diverse cloud and on-premises environments. Despite its efficiency and traffic isolation features, MPLS does not offer encryption by default. This can be a significant security concern, particularly when data traverses shared provider infrastructure or when compliance requires encrypted data in transit. In such cases, administrators may configure IPSec tunnels over MPLS links to ensure data remains confidential and tamper-resistant. The exam may present use cases where additional encryption is required, prompting the use of IPSec even in an MPLS environment. Troubleshooting IPSec tunnels involves examining several common failure points. Misconfigured pre-shared keys or mismatched policies between peers are frequent causes of negotiation failure. Network address translation, or NAT, can interfere with the tunnel establishment unless special considerations like NAT traversal are implemented. Tools such as packet captures, debug logs, and Internet key exchange diagnostics are essential for identifying where the process fails. Cloud Plus candidates must know how to approach tunnel failures methodically and restore secure connectivity without compromising policy. MPLS networks, in contrast, offer built-in resiliency features that automatically reroute traffic in the event of a failure. If a primary label-switched path is disrupted, the network dynamically shifts traffic to an alternate route, often within milliseconds. These capabilities are governed by service-level agreements, which define expected uptime, response time, and failover behavior. While the consumer has less visibility into these mechanisms, understanding their function is essential for planning business continuity and disaster recovery strategies in cloud-connected environments. The Cloud Plus exam includes protocol-specific questions that require comparing IPSec and MPLS in deployment scenarios. You may be asked to choose the most suitable protocol based on criteria like encryption requirements, bandwidth guarantees, or management responsibilities. Some questions will focus on the differences in tunnel setup, such as IPSec's need for matching security policies versus MPLS's reliance on pre-established provider paths. Understanding when to use each protocol is a core exam competency. Vendor integration and cloud limitations are practical concerns when selecting a protocol. Not all cloud providers offer direct MPLS integration without the use of partner-managed services. IPSec, however, is almost universally supported by virtual network gateway services and is often available through native deployment templates. Cloud architects must consider the native capabilities of the platform they're designing for and whether third-party services are needed to enable MPLS connectivity. When selecting the right protocol, several factors must be weighed. IPSec is typically better for self-managed deployments where end-to-end encryption and granular policy control are required. It scales well with dynamic workloads and is cost-effective for short-term or flexible deployments. MPLS, by contrast, offers predictability, consistent latency, and enhanced quality of service, making it ideal for applications with stringent performance requirements. Scenario-driven decisions should guide protocol selection, and candidates must evaluate the architecture's needs before making a recommendation. Another key distinction between the two protocols is the level of operational visibility and control. With IPSec, administrators manage every aspect of the tunnel, from encryption policies to authentication and routing. This provides flexibility, but also requires technical expertise. With MPLS, much of the control resides with the provider. While this reduces complexity for the consumer, it also limits customization. Cloud Plus candidates must understand these differences when evaluating trade-offs in visibility, responsibility, and flexibility. To summarize, both IPSec and MPLS are vital components in cloud and hybrid networking strategies, but they serve different functions. IPSec secures data through encryption and is fully managed by the enterprise. MPLS enhances transport performance and is typically provider-managed. Choosing the appropriate protocol depends on the use case, compliance needs, and desired control. Cloud Plus certification demands a clear understanding of both technologies to ensure that connectivity designs are secure, efficient, and aligned with business goals. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.